Okay, our next speaker is Margaret Gardner from the University of Pennsylvania, and she'll be speaking about ComBatLS, a location and scale preserving method for multi-site image harmonization.
All right, thank you so much for having me. So my name is Margaret. I'm a graduate student, and today I'm going to be talking about ComBatLS, which is a new location and scale preserving method for data harmonization. So recently, there have been some really cool efforts from the group that I'm in, as well as others, to compile structural MRI scans from individuals of all ages, and then use that data to create brain charts. And if you haven't made it to any of the other talks this week that have been talking about normative models, these work just like pediatric growth charts for height or weight. So what they do is we're tracking the normative trajectory of a phenotype, so in our case that would be a brain structure feature, over a covariate like age. And these are really great because they show you not just the normative trajectory in the population for this phenotype, but they're also modeling the variance or the spread in the data at every level of our covariates. See there. And so this allows us to derive a centile score for each individual, showing where they fall relative to their peers. So this person highlighted in red looks like they're in about the 5th percentile on this feature. And we can use centile scores like these to see if having an extreme centile like this one is associated with potentially a clinical diagnosis. But again, fitting these models requires a lot of data at every age across the human lifespan. And really the only way to be able to do that is to combine data from different sites and different studies. However, this then causes its own set of problems in the form of site or batch effects. And these are artificial differences in data that's collected at different sites. And it can be because you have different MRI scanners, different acquisition sequences, things like that. And these are all things that we want to be able to remove in order to recover the true data. However, sites can also have real differences that we want to preserve. So for example, this blue site that's farther to the left, it looks like those subjects are a little bit younger than the ones in the other sites. And we want to be able to keep whatever effect age might be having on this feature when we're correcting for side effects. So one really popular and effective way of doing this is a method called ComBat. And it first estimates the effects of any covariates that you choose, so again, like age, and then preserves it when estimating and removing those nuisance side effects. And this has been extended to create ComBatGAM, among others, which allows you to preserve nonlinear covariate effects as well. So as you can see, we're definitely getting closer to the true data, but one thing that's still different is the spread, where the true data has more variability in the higher age ranges and less variation in the younger subjects. And this is because biological factors like age and sex are known to affect the variance or scale of a brain feature's distribution across the population. So for example, this is from a really cool paper by Laura Warenga. They use data from the UK Biobank to model differences in brain structure variances between males and females. And here blue indicates features that have greater variance among males. So what this means for a multi-site study is that if you have one site that has maybe more males, one that's kind of even, and then one that's more females, you're actually going to see differences in the variances of the data you collect at each site. And we created ComBatLS to be able to address this issue during harmonization. So we worked off of ComBatGAM, which again uses generalized additive models to preserve both linear and nonlinear covariate effects on the distribution's means or locations. And we updated this to use generalized additive models for location, scale, and shape, or GAMLs, to estimate our covariate effects. And this encompasses a model for location or mean, similar to ComBatGAM. Then it also directly models the covariates effects on distribution scales. And this gives us an estimate of how biological covariates, like age or sex, affect the feature scales, which we can then allowing us to preserve these effects when we harmonize. So returning to our example, if we're harmonizing with ComBatGAM, it's going to force all of these sites to have the same variances. And then the idea of ComBatLS is that it will preserve sex's effects on scales, which again, we're going to need in order to create accurate brain charts. So first, we wanted to test that ComBatLS can actually preserve these scale effects across imbalanced sites. So to do this, we used brain structure data from participants in the UK Biobank. And then we subsampled them into 3 different groups to simulate different collection sites. One that has an even ratio of males to females, one that's 4:1 females, and one that's 4:1 males. And next we applied our new method, ComBatLS, as well as 2 existing methods, ComBat and ComBatGam, to harmonize across these simulated sites. And again, it's important to note that because subjects are randomly assigned to these simulated sites, there's no actual batch effects that we're looking to harmonize. So any differences in these distributions are the results of the uneven distribution of sex, and again, things that we want to preserve. Okay, so next we took these 3 harmonized data sets, as well as the original data, and we fit brain charts for 208 brain structure features. And then we use these brain charts to derive centile scores for each individual. And again, there's no batch effects here, which means that if a ComBat method is doing a good job of preserving covariate effects, these brain charts over on the right and the centiles that we get from them are going to look just like the ones from the true data in black. So we quantified this by taking the differences in subject centile scores when using each ComBat method and their true centile scores, which we quantified as centile error, and used this as a metric of how well sex's effects are being preserved. We calculated each subject's centile error for all of our brain features, and then compared these centile errors distributions across ComBat methods. So again, smaller errors equals better covariate preservation. And we replicated all of this 100 times to account for the randomness in our sampling. So first, just to visualize, what I'm showing here is the brain chart that we derived for ventricular volumes in males and females. And the black dotted line shows the true values corresponding to each percentile in this population, which we got from the raw data. And then the different colors show where these lines were estimated when we used the data that have been harmonized by the different versions of ComBat. So zooming in on the 50th percentile, you see that no matter what version of ComBat you use, they're all doing a pretty good job of mapping this median trajectory. However, if you look at the 95th percentile, where we might expect to find more individuals in clinical groups, you find that ComBat, which is in green, and ComBatGam in blue, are slightly underestimating where that cutoff is for males and overestimating it in females. Meanwhile, we see that ComBatLS, which is in yellow, is still right on target. And then this becomes even more evident if you move somewhere more extreme, like the 99th percentile. So again, to quantify this effect, we looked at these errors and centile scores derived from these brain charts, and we see that ComBatLS comes the closest to recapturing true centile scores with the smallest absolute centile errors. And this is shown here for our 4 global tissue volume features. And these centile errors are consistently small across brain structure phenotypes when we use ComBatLS, which is down here on the bottom, and darker blue is indicating regions of larger median centile errors. So what's really exciting is that these results held across all of our replications for the vast majority of brain features, and when we varied the ratios of males and females in each of our simulated sites. So great, all of this is showing that ComBatLS does the best job of preserving covariate effects, which is very exciting, and we need those to get accurate normative scores. However, we still needed to see whether ComBatLS can actually harmonize data, which is what we wanted to do in the first place, is get rid of those nuisance side effects. So we use structural MRI data from the Lifespan Brain Chart Consortium. So we have about 52,000 subjects, ages 3 to 100 years after QC. And then we applied ComBatLS and ComBatGam to harmonize across these studies. And what we find is that both our new method, ComBatLS, and the established method, ComBatGam, are really comparable in their ability to remove batch effects and centiles in these data. However, just like in our simulation study, there are subtle differences in centile scores derived from the 2 different methods. So one of the things I mentioned earlier is that centile scores are sometimes used to see if someone who's at an extreme end of the distributions, so for example, below the 5th percentile or above the 95th percentile, is at risk for a disease. And we wanted to know how the choice of whether to use ComBatLS versus ComBatGam would affect analyses like these. So what we did was we found all of the extreme features, so the ones at either end of the distributions, according to our ComBatLS derived brain charts and our ComBatGam brain charts. And we just looked at how often they disagreed. So this is showing the number of subjects whose categorization changed over on the y-axis across features which are shown on the x-axis. And so it is really important to note that we do not have the ground truth for these data of what they should look like in a perfect world where they're harmonized. But if because of our simulations, we think that the centiles we get from ComBatLS are more accurate, then you can think of this plot as showing all of the false positives and false negatives that you would get just from your choice of harmonization. We found that there was an average around 1 false positive or false negative per subject, which could potentially affect downstream analyses. So in conclusion, ComBatLS preserves covariates effects on both location and scale during harmonization, which produces more accurate normative scores when harmonizing across imbalanced samples and effectively removes batch effects in real-world consortium data. So we want to welcome you all to go ahead and give it a try. ComBatLS for R is available at the link here, and once our preprint is up, we will be adding that as well. You can also find me at my poster later, or chat with any of the lovely people who are pictured here who made this possible. Thank you so much.
Thank you. We have time for one, maybe two short questions. First, what are the caveats when applying ComBatLS to small sample studies, or how many samples would you need per data set?
Yeah, so one of the cool things about ComBat and like all of the extensions is that it uses empirical Bayes in order to estimate what side effects would look like in sites that have fewer samples. So there are actually there's a site in here that we harmonized that only had 5 subjects. That said, it's also because it's borrowing information from the other batches that you're harmonizing. It's kind of a function of how small your smallest site is and how many sites you have and how big they are. I guess another caveat that would be to note, though, is it's, ComBatLS, like all the other methods, rely on you pre-specifying different covariates, so you do need enough variation in the different covariates that it'll actually be able to estimate those effects. It can't preserve what it can't estimate.
Okay, so that's all the time we have. Please visit the poster in the afternoon session. Thank you once again.